Here's this. We're going to continue our series on LSTMs, on recurrent networks. We're going to talk about stability and memory of recurrent networks. Here's what we've seen so far. Iterated structures are good for analyzing time series data with short time dependencies in the past. This is what we call time delay neural networks. And we also saw that recurrent structures are good for analyzing time series with long-term dependencies on the past, because you want to have something that remembers things all the way to the beginning of time. Now, the assumption over here is that whatever it is you're trying to store will be held by the network, that the network structure is sufficient to keep track of everything till the end of time. This may or may not happen. We'll see how this works out. But before that, we're going to ask, see something interesting. Recurrent networks are good not merely for analyzing time series problems. They're also good at other things. Does anybody have the number 100? Okay, this is your turn, right? So suppose, what's your name? Neeraj. Okay. If I want to build a network to add two n-bit numbers, what sort of network will it be? How many units will it have? So here is the problem I have. I'm going to have two n-bit numbers. I want the network to take all of these and produce an output. So if I decide that it's going to have only two layers, how large is the network going to be? Order of magnitude. Can you guess? So who was it? There was Neeraja, right? Yeah. So can you speak up? And who's 104? Anyone got 104? Okay, nobody yet. This is not working out, right? 99? You guys are horrible. Okay, I'll keep calling out numbers till I find one. Let's see. In the meantime, if you don't want me to waste time, does somebody else want to take a shot at how many neurons would this take? Pardon me? N plus 1? No. So that's n. You have n plus 1 outputs, but how many will you have in here if I decide, for example, to have only 2 layers or 3 layers? It's going to be exponential in n, correct? A summation is just an XOR. So this is going to be very, very large. Now, can this person who's got 21 speak up? I think we didn't. Yes, okay. So Gopi, if I want to train this network, how many inputs will I have to provide?
At least exponential to the e of n.
So how many inputs will I have to provide to train this network? Continue.
2 raised to n.
2 raised to n?
Yeah, because
I'm adding 2 n-bit numbers.
Yeah, because each are finally will need at least
2 raised to 2n at least, to be precise, right? So just to train this network is going to be exponentially large, and to want to make sure that the network actually recognizes every pattern, every input pattern, and learns to produce the correct output, you're going to need an exponential number of training instances. Now suppose I want to do the same thing with recurrence. Who's 17? Did anybody get 17? No? Okay. Yes. Okay, 17. How many neurons would I need over here? Yes. You need 2n? You don't even need 2n, right? The network is just going to be one network which produces an output and produces a carry. That's it. Correct? And you can do this, you can just chain it, and that's what a recurrent network does. So this is going to be the first bit of the pattern A. This is going to be the first bit of pattern B. So A1, B1, then A2, B2, A3, B3, and so on. So I can just chain the same unit. This is a recurrent network, is it not? Does everybody agree that this is a recurrent network, right? How many instances will I need to train this network? Pardon me? Input. How many training inputs will I need? Pardon me? No, because this is just being recognized on one bit, correct? You're going to need 4. That's it. You're going to say what is 0, 0, the output is 0, the carry is 0, 0, 1, the output is 0, 1, the carry is 0, 1, 0, the output is 1, the carry is 0, 1, 1. This is the input, this is the output. With this table, you will be actually able to train the network. So as you can see, just going from a recurrent network can actually do what an MLP is supposed to be able to do. And you should be able to train, if properly configured, you should be able to train this with far lesser data than a regular MLP would require. Same thing with the parity problem. The parity problem, again, is an XOR problem, right? How many neurons did we need to train this network if we had a fixed size? Can somebody? Who is 13? Yes, how many will we need? We went through this XOR exercise, right? What did the XOR exercise say in the lecture 2? If I want to train an XOR network for just n inputs, how many neurons did we need? It was 2 raised to n. It was exponential unless you allowed it to become deep, in which case it was linear, right? And how many training instances would I need over here? If I had to train the network, it has to learn about every possible input pattern. So what is the answer then? There's only one n, right? So basically, you're going to have to see, for the XOR network, you want to see every possible input pattern, and you want to get the output over here, right? You need, how many of these would you have? If it's an n-bit input pattern? 2 raised to n. So once again, you're going to need 2 raised to n training instances to train this network. Suppose I did this with a recurrent network. Then how many would I need? Who's number 1? There's no numero uno in the class. So that's you. Perfect. Yes. Tell me. If I were to train this with recurrent networks, how many neurons would I need? How many training instances would I need? And how many neurons would I need? Can you guess? So it's going to be 1 block per bit. It's an XOR, right? So it's an XOR network. We saw that we could do this with only 3 neurons, correct? Maybe you want to have something that's carrying out. Actually, you don't even need to carry out. So what you would really need is 1 XOR per bit, except that this output goes back in. Is that making sense? Right? You match the first 2 bits. If the first 2 bits match, the output is a 0, and if not, the output is a 1. The output of that can be XORed with the next bit, because that's how the XOR operates. It's a sequence of XORs, right? And so you can just chain it. And Manasi, in this case, how much training data would I require? How many bits is my basic unit? Pardon, can you speak up, please? 2, right? So how many training instances would I need? 4. So you can see that going from a recurrent network, from an MLP to a recurrent network, can actually make problems that nominally are intended for MLPs to become much simpler. You can do the whole thing by using the recurrent structures in the problem setting to come up with much smaller networks if you're doing this recurrently. So here's the first poll. This thing is slowing us down, but I've got to keep trying. These are the remaining slips. Those two?
Oh, no. This is blank.
All right. Thank you, guys.
No.
Which side is the one I called? This. Do we have time? Thank you. All right, guys, I think we're out of time. 5 seconds. I'll skip that. Both of these statements were true, as we just saw, right? Moving on. So recurrent structures can be trained by minimizing the divergence between the sequence of outputs and the sequence of desired outputs. We saw this also in the last class. And maybe, do we have a person who's 98? Nobody is 98, so I'll answer this question. I'll beam this question out to public. Is this the same as the sum of the divergences at individual times? No, right? This is actually the divergence between two sequences. And now let's go back to this question of recurrence. What kind of model was this? Is this a recurrent model? Okay, if it's, who's 95? There's no 95. Is this a recurrent model? No, right? This was a time delay neural network. Now, let's assume that the input is always bounded, meaning the input never becomes infinite. Will the output, the weights are also bounded, will the output ever become infinite? Yes or no? Who's 112? So will the outputs become infinite? No, right? Because everything is bounded. Every single step over here is bounded. This is what is called a bounded input, bounded output model. It's BIBO or BIBO stable. Now, what about this guy? Is this going to be BIBO? Anyone with 78? Maybe. Okay. Is this going to be BIBO? Yes or no? Somebody speak up. You guys can't be so silent. I'll wait. Is this going to be BIBO? No. Why do you say it's not? Depends on? Depends on the number of time steps. Is that always going to be the case? So, first, if my activations are bounded, for example, if I were using sigmoids, there's no way the output is going to become infinity. So for bounded activations, this will be bounded output. Is that necessarily the behavior we want? No, because this could just saturate, right? So the issue we're really dealing with is how does this behave? Now, of course, once we begin talking about nonlinear activations, we run into other issues. So I'm going to dispense with this for now because most of you don't seem to have got the slips, but maybe I'll call out names. The thing is, we still want to figure out if and when this will blow up, or if it's not blowing up, if it will saturate. Now, nonlinearity introduces complexity. So we're going to start off by analyzing linear models, which means we're going to assume for now that, again, all of the memory is being held by the green layer, the recurrent layer, correct? So we're going to assume for now that the recurrent layer only has linear activations. So what I mean by linear activations, and I'm going to assume a single hidden layer for simplicity. And the reason I'm going to be looking at linear activations is the famous streetlight effect. Linear models are what we can actually analyze. Those of you who came in at the back, please pick up some slips. There are slips of this kind that each of you must get, okay? Yeah. Now, so here's what a linear activation neuron is going to look like. At each neuron, you just compute an affine function of the input, but there's also a bias plus b. The plus b is missing over here. This is the affine function of the hidden state at the previous time and the input at the current time. The output itself is simply the input because there is no further activation. This is a linear activation. So now let's see how this works out. At time k, there's always a plus b. Okay, I keep missing the plus b, but let's ignore the plus b for now, right? Let's just assume pure linearity. Then that's what we're going to do to analyze what is going on. So at time k, I'm going to say that the activation, the hidden output is, again, remember the activation is linear, right? Is some WH times HK minus 1, which is the recurrent weight, plus WX times XK. So again, remember this was how we drew this. So I had, let me see if I can get this guy down. This was how we drew this. We had each unit, this is HK, and this is getting HK minus 1 with, and this is XK with WX, right? So if this is the structure at the recurrent time, HK is WH, XK, HK minus 1 plus WX, XK, right? I can write HK minus 1 as WH of HK minus 2 plus WX, XK minus 1. So now, who is number 10? Yes, okay. Can you write this thing, that equation on top, without referring to HK? Without referring to HK minus 1. What would it look like in terms of HK minus 2? Pardon me, can you speak up? I can just plug the second equation into the first, can I not? So what will that be? Okay, this is not working. Let me answer for you guys, right? Whoever gets the next one must answer, otherwise shame on you. So I can write HK equals WH squared HK minus 2 plus WH WX, what is that? XK plus WX XK minus 1, right? Now, suppose I do not want to refer to XK minus 2. Anybody get 88? Okay, so if nobody has 88, I need a volunteer. Someone raise your hand. Okay, I want you to write that HK in terms of XK minus HK minus 3. What would that be?
WH times WH to the third HK minus 3.
Yeah.
Plus WX times the sum of XK minus 1, XK minus 2.
So what would that come out to be? That's going to come out at XK minus 2, right? I think that's what it comes out as. WH XK WX XK minus 1 plus WX XK. Actually,
There's no square, is it?
yeah, so basically I'm just going to be plugging in the same term over here. I'm in here, I'm going to be writing a WHK minus 2 equals WH HK minus 3 plus WX XK minus 2, right? So if I just plug it in, I get this formula. I can keep extending this, and when I finally write this out, I'm going to get something of this kind, which says that the kth output, now observe the series, is going to be WH raised to k times WX x0 plus WH raised to k minus 1 times XK WX x1. Observe that this entire sequence is in terms of x's except for the very initial value, which is this guy, the initial step. All I did was expand it out, nothing complicated. Now, if I just think of this guy over here, what is this term over here? If I have a sequence at if I have time t, and if I have an input x0 over here, then the contribution of x0 at the kth time is simply going to be wh raised to k wx x0. The contribution of x1 at the kth time, this distance is now k minus 1, right? For this guy, that's going to be wh raised to k minus 1 wx x1. What would the contribution of x2 be using the same sequence? Can the person who's 84 try to guess? Who's 84? Nobody? What would it be? That's going to be wh k minus 2 wx x2. So you see what is happening, right? If I am able to define this one thing, what is the output in response to an input at time 0? What's the output at time k? I can use the same formula to write the response for an entire sequence of inputs. Now, if this guy over here on top, if any of these subsequent terms blow up, will that first term blow up? So basically all I need to analyze is what happens with the circle guy, right? So there's a vector version of it, okay? So I'm going to just analyze what happens to the system response when I have just a single input at time 0 and I'm looking at the response at time k. So here is what we got. We generally, if I write it in terms of w and c, if I had an input at time 0, the response at time t, so h0 of t means the response at time t when the input is at time 0, okay? That's going to be of the form w raised to t c times x0. We just worked it out. I've just sort of changed the notation, right? What can you tell me about what happens to a single response at time 0 over here? Will that stay stable? Will it be remembered continuously? What will happen? Can anybody tell me what will happen over here? Who's 81? Who's 18? There's no 18 or 81, right? So what would happen if w were greater than 1? Would that remain constant? So if w it would blow up. If w were greater than 1, w raised to t, it's going to blow up. What if w is less than 1? It's going to die down, right? How fast does it die down or blow up? Does that depend on x? No, right? So the basic thing is the ability of the network to hold on to some thought, some input, does not depend on the network itself, on the input. It only depends on the network parameters, right? Now I can do the same thing. I've been too slow. I can write the same thing in terms of vectors. All of this was, thinking of a simple scalar operation. But if you write it in terms of vectors, here's what you get. If I have a single response at 0, and w is the recurrent weight matrix, then you're going to find that the hidden response at time t is w times raised to t times whatever weight matrix you apply to the input times the input at time 0. Now, this guy, these are matrices, so they're not as simple to analyze maybe as scalars. But any matrix w can be decomposed in terms of, we can perform eigenanalysis on it and just write this as u lambda u inverse, standard eigendecomposition of a matrix, right? And the matrix U comprises a sequence of bases that span the space. So as a result, I can write any vector as a linear combination of the columns of U. And now the properties of the columns of U is that if you multiply any ui, any column of U by W, this is eigendecomposition. That's simply going to be lambda U, correct? So this is this famous expansion. If I take any x prime and I multiply it by W, if you look at what happens, all that happens is that each of these coefficients simply gets multiplied by the corresponding lambda. If I multiply it by W a second time, so I have WU I equals lambda I UI. If I take any vector x, and if this is A1 U1 plus A2 U2 plus A3 U3, then if I multiply this, is there an eraser? Yeah. If I multiply this by W, then this is what will happen. The Wx is going to be A1 WU1 plus A2 WU2 plus A3 WU3, correct? Which is simply going to be A1 lambda 1 U1 plus A2 lambda 2 U2 and so on. If I multiply this by W a second time, what happens? This is going to be again W times U1, so this simply gets, each of these lambdas gets squared. If I multiply this by W t times, you're simply going to get lambda raised to t, right? Now what will happen to this guy as t becomes larger and larger? You're exponentiating the eigenvalues, correct? If I have start off with two eigenvalues that are very close, after exponentiating both of them a very large number of times, which one will remain? The larger one. The smaller one is simply going to vanish, right? So in the limit, all you're going to be left with is the component corresponding to the largest eigenvalue. So if you simply want to analyze how this behaves, for any input for large T, the length of the hidden vector will expand or contract according to the tth power of the largest eigenvalue of the recurrent weights matrix. And now, if this is greater than 1, the response is going to blow up. If it's less than 1, it's going to shrink. Yes, Kunal?
Wouldn't this be true only if UI span the domain of X? Like you cannot always, right? The UIs will not always span the domain of X.
It's eigen decomposition. Your UIs are going to span the space. The lambdas may be 0.
You have to span the space for W, but for X, span the regular linear combination of the UIs.
If they span the space, any X can be written in terms of the UIs, right? So here's what will happen. Here, I have this simple linear recursion. And here, lambda max is 0.09. Here, lambda max is 1.1. Lambda max is 1.1. You can see that when the largest lambda is 1, you get some kind of stability in this case, right? It doesn't mean, so even here, why does it go down initially and then become stable? Anyone want to tell me? Here's what happens, right? If you look at this equation, it takes some time for the remaining lambdas to die. So initially the thing will go down, and then the length of the vector is going to stabilize. If lambda max is greater than 1, that one is going to blow up. If it's less than 1, it's going to die. And then you have multiple plots over here. So can anybody tell me why this thing is wiggling? Anybody? Yeah.
Because if the absolute value is like 1, if it's negative 1, then it becomes flipping signs.
It has to do with the fact that the eigenvalues can be complex. So then you get oscillatory behavior. But nonetheless, here's the general trend. If the largest eigenvalue is greater than 1, it's going to blow up. If it's less than 1, it's going to. If it's 1, it's going to be stable. If it's less than 1, it's going to disappear. Okay? So in linear systems, long-term behavior depends entirely on the eigenvalues of the recurrent weights matrix. If the largest eigenvalue is greater than 1, the system blows up. If it's lesser than 1, the response will vanish very quickly. Complex eigenvalues can cause oscillatory behavior, but with the same overall trends. Now here's the key bit. The rate at which what is being held by this hidden state blows up, or the rate at which it sort of vanishes to 0, depends only upon the recurrent weights and doesn't depend on anything else, right? So it doesn't depend on the input. Now we are looking at linear activations, but in a real network you're not going to have linear activations. You're going to have some kind of non-linearity to go with it. So let's take a look at what happens when I introduce a non-linearity. Here's what we have. The hidden layer is going to be some, say, we will look at different activations. First, we look at sigmoids. The sigmoid acts on an affine combination of the previous, the hidden state of the previous time and the current input. and there's a bias B, right? So in this case, we're looking at a scalar thing. So everything is scalar. So I just have a scalar weight. Here are 3 different values for the weight. And in each plot, I have 5 curves, therefore 5 different values of the bias. And these are 3 different values of x0. So the input at time 0. And this is what happens with iterations. I'm showing iterations 0 to 20. What do you see about these 9 plots at time 10? Can anybody tell me? Are these things different after time 10? No, right? What does the final output depend on? It only depends on B, right? Regardless of the weight, regardless of the input, eventually the value that's remembered is just the bias, right? Same thing with tan H. Now, here observe how quickly, in less than 4 time steps, everything about the input is forgotten, right? If I look at tan H, you still get the same kind of behavior, except it remembers things for a bit longer, for about 10 time steps. If I look at ReLUs, ReLU activations, things either die or they blow up. There's never any stability at all, right? Now, this is assuming that all the hidden activations are scalar. But if you're looking at vector activations, pretty much the same behavior results. In this case, I've got H equals the activation times W, HT minus 1 plus CX plus B. HT minus 1, XT, and B are all vectors. And what I'm plotting is the length of the hidden state vector, H. And once again, you can see this one is for sigmoids. You can see that regardless of the input, I have different inputs on the different rows. The eventual pattern that arises that you end up in every case, if you look at it closely, the Y scales are different. The eventual pattern that you end up at only depends on the network parameters. It doesn't depend on the input. Of the different activations, the only activation that actually remembers anything for a significant period of time is the tan H. The ReLU is quite useless. Things blow up or die. The sigmoid doesn't remember anything at all. So, which is why when you build recurrent networks, your hidden state activations tend to be tan H's, because those are the ones that remember something about the memory for the longest amount of time. But even so, after about 10 time steps, they're quite useless. They don't remember anything. They just sort of go to a value which does not depend on what the input was. It only depends on the network parameters. So you can actually run formal stability analysis, and for that you'd have to consider the convergence of Lyapunov functions and Routh's criterion and so on. We don't need to go through all of this. The lessons are quite similar, quite simple. If you have bipolar activations like the tan H, then these things sort of tend to remember the input a little longer than other ones, than things like sigmoids or ReLUs. But in every case, what is remembered is dependent on the eigenvalues of the weights matrix and the bias. The best case memory is short, and in all cases where the network eventually arrives at depends on the parameters of the network and not very much on the input itself. So the point of going to recurrent networks was that we wanted this network to remember something about the infinite past. We started our whole entire lecture with the motivation that if I'm trying to predict stock, you guys in the back, can you shut your laptops? Yeah. So we started off with the assumption that if you want to predict make predictions about the stock market, you should be looking back into infinite history. And will this really be looking at infinite history and remembering anything about it? Right? Can you say that aloud, all of you? No. Okay, because some of you are not paying attention, right? So the last row didn't say no. So maybe I can repeat this with the last row saying no. Okay. Next time I ask you for a no, yes or no, you'll have to say no. Here's a poll. Okay, 5 seconds, guys. Okay, we had 2 questions. I asked you many different things about how the recurrent network behaves. It turns out that how long the network remembers anything depends on the weights of the recurrent layers, the bias of the recurrent layers. It depends on the activation, but it doesn't depend on what was remembered, what it's trying to remember. Also, what the network remembers, so there are 2 different things, how long it remembers it and what it remembers. That too is dependent on everything except what it's trying to remember. So there's no memorable input that the network will try to hold on to. Everything and anything is being treated just the same and forgotten pretty quickly. This is not the kind of behavior we want, right? So.
But in the graphs, this kind did not depend on the weights, right? For all weights, it stabilized in a.
It depends on the eigenvalue of the weights matrix. So the eigenvalues are, I have a couple of different, I glossed over it. But this is with eigenvalue 1.1. You can see the behavior. And you can look at the tan H in particular. And this is with eigenvalue 0.9. And you can see that it behaves. It depends only on the bias and the eigenvalues of the matrix, weights matrix. So the story we have so far is that recurrent networks are supposed to retain information about the infinite past. In practice, they tend to blow up or forget. If the largest eigenvalue of the recurrent weights matrix is greater than 1, the response may blow up. If it's less than 1, it may die down very quickly. The memory of the network depends on the parameters and the activations of the hidden units. So sigmoid activations saturate, and then the network cannot retain more information because they saturate. ReLU activations blow up or vanish, so they are utterly useless in the hidden activations. And tan H activations are slightly more useful in retaining long-term memory, but they're not all that much. Now, so the summary of everything we've seen so far is that RNNs are supposedly excellent models for time series analysis, like prediction, classification, and sequence generation. They can even simplify some problems that are difficult for MLPs, but the memory is not all that great. Now, we have a second issue, a particular problem with training deep networks. And this is not just recurrent networks, this is true of all deep networks. And this has to do with the fact that the gradient of the error with respect to weights is unstable. So let's go back and look at the network a bit more carefully. If I have a network of this kind, then the first layer output is a function of the inputs. The second layer is a function of the output of the first layer. It multiplies the output of the first layer by a weights matrix and then applies an activation to it. The third layer output is a function of the output of the second layer. So when I get all the way to the end, the network is just a nested function. The outermost activation, which applies to the weights of the outermost matrix, multiplying the next level activation, which works on the product of the weights for that layer and the previous activation, and so on. There are some bias terms which have sort of left out to simplify things. And the final divergence is a function of the output of the network and the desired output. So this too is a nested function. And then we know from the chain rule that we saw earlier that when I have something of this kind, f of w of g of x, then the derivative of f with respect to x is going to be the derivative of f with respect to wgx times the derivative of wgx with respect to g of x times the derivative of g of x with respect to x, right? If these were all vectors, this is bad notation, but the general concept holds. And if I write wgx as some z, then in vector notation, this whole chain rule is going to be this first term is the derivative of f with respect to z. The second term is the derivative of z with respect to g, which is just w, right? And the third term is the derivative of g with respect to x. So does everybody see how this works, right? For the longer network, for the deeper network, the divergence is a function of a nested function of many functions, starting off with the divergence function itself, and then the activations and the weights of each layer. So if I write out the derivative of the divergence with respect to the output of any intermediate layer, say the kth layer, this derivative is going to be the derivative of d with respect to its argument. When I just write nabla d, it means the derivative of d with respect to everything that comes within the parenthesis. Okay? So this is going to be the derivative of d with respect to its argument times the derivative of fn with respect to its argument times the derivative wn, as we saw earlier, times the derivative of fn minus 1 with respect to its argument times wn minus 1, and so on. So basically, as you keep now what is this guy here? What is the this derivative of f of n with respect to its argument? F of n is an activation function, right? So this would be, what would this be? Can somebody wake up and tell me? So what is that called? We call it a Jacobian, remember? So this is going to be a Jacobian. So it's on the slide, come on. So basically, the derivative of the divergence with respect to the output of some intermediate layer is going to be a sequential product of Jacobians and weight matrices. So here's what we've got. Things are alternating. You have first the derivative of the divergence function itself with respect to the output of the network. Then you have the Jacobian of the output activation function. Then you have the weights layer of for the output layer, then the Jacobian of the previous layer, then the previous layer's weights, and go on and so on. Now, what kind of suppose I have an n output and layer which has n outputs. What is the size of the Jacobian? It's square, correct? Now, if I have scalar activations, not a softmax, but every neuron is applying independently to its inputs, then what is the structure of that Jacobian matrix? Pardon me? No, it's still n. It's still n by n, but what? It'll be diagonal, right? So in this case, it's going to be a diagonal matrix where every diagonal term is simply the derivative of an activation function. Now, what can you tell me about this activation function? Let me pull out one more number. Is there anybody here who is 92? No? Let me try a few numbers here. So 8, anyone with 8? This is horrible. Yes, you are 8. Fantastic. So what is the largest value of the derivative of a ReLU? Can you tell me? So what is the ReLU activation? So the derivative of the ReLU is going to be 1, right? Always? When it's positive, it's 1. When it's negative, it's 0. So the largest value of the derivative of a ReLU is going to be 1. Okay. Who's 23? Look at your numbers, guys. Who's 23? Anybody with 23? No? Okay, let me try a couple of numbers more. 49? Nobody got most of these numbers, right? We'll be more careful in the next class. Okay, what is the largest value of the derivative of a tan H activation? Oren?
I don't recall.
It's going to be 1, right? What about a sigmoid? A sigmoid is going to be 0.25, okay? So here is what we get. This is the derivative for a tan H. The largest value is 1. And remember, we wanted to use tan H activations for the hidden layer, correct? So the largest value of f prime of x, the diagonal term, is going to be 1. If you used other activations, it's going to be less. If I multiply a vector by this matrix, will the length of the vector increase? Will it remain the same, or will it shrink? It will shrink because every term is being shrunk, correct? So what this means is that multiplication by the Jacobian is always a shrinking operation. Now, when you compute the derivatives going backwards, every second step over here is shrinking the length of your derivative. Okay? What about these guys, these weights? What can you tell me? Suppose I take any arbitrary vector and multiply it by a matrix W, what will happen to the length of V? Can anyone tell me? Who is number 108? Yes, what would happen? Will it always get smaller? So what are the conditions? Anyone else have an answer? It depends on the singular values of the matrix, right? Have you heard of the term singular values? No. Okay, so here's what will happen if I multiply a, let's just take a single simple two-dimensional case. Suppose I multiplied every point on a circle by a matrix. The result is going to be an ellipse of some kind, and these maximum and the major and minor axes of the ellipse, the length of these, if the original circle has a radius of 1, then the lengths of these guys are the singular values of the matrix, which means the largest amount by which a vector is going to get scaled up is going to be the largest singular value. The smallest amount by which it's going to be scaled up or down is the smallest singular value. Is that making sense to everybody? Right?
Can you repeat the transformation that was made between those two?
If I'm just multiplying, so I'm looking at every vector on this circle, V. I'm multiplying it by a matrix W, and the result is going to be a 2 cross 2 matrix W in this case. The result is going to be an ellipse. And so what will happen is that this vectors are going to be increased in length or shrunk. It's a linear transform. The circle will become an ellipse. You have major and minor axes. The lengths of those major and minor axes are your singular values, which tells me that the largest amount by which the vector can scale, the matrix can scale a vector is its largest singular value. And specifically, corresponding to each singular value is going to be a singular vector. Here there'll be 2 of them. So anything that falls in this direction is going to get scaled up by sigma max. Anything that falls in this direction is going to get scaled up by sigma min. Okay? So if the largest singular value of your weights matrix is less than 1, what will happen when I multiply a vector by this matrix? It's going to shrink, right? If the largest singular value is greater than 1, what happens? It doesn't always blow up, because if I think of any vector over here, some arbitrary vector, that's going to be some linear combination of these 2 guys. The component that's in this direction is going to blow up. The component that's in the remaining directions is going to shrink. Make sense? And so here's what will happen. Repeated multiplication by the weights matrix will result in gradients either simply zapping down or blowing up in very specific directions. Now what we really want to look at is layer-wise computation. At each layer, you're multiplying, when you're performing backprop, you're multiplying the derivatives by the Jacobian and then the weights matrix. So if you look at the product of the Jacobian and the weights matrix, we are assured that the Jacobian will always shrink the vector. The weights matrix may scale up some directions, but the majority of the directions it's going to shrink things down, because if you take any random matrix and you look at its singular values, it will have a very small number of singular values greater than 1. The majority of them are going to be less than 1. So 1 or 2 directions will grow, the rest of them are just simply going to disappear. So as a result, here's what will happen. As you go back from the output to the input of the network, the gradient that you had is going to keep shrinking and shrinking and shrinking in most directions, and some components are going to get blown up. So by the time you get to this layer, the majority of the derivatives you have are going to be tiny or vanishingly small. A small number are going to be very large. Making sense? Right? So you end up with what are called vanishing or exploding gradients. This is a consequence of the simple nature of the arithmetic over here. And to see, and of course, as the network depth increases, this happens exponentially fast. The vanishing and explosion happens exponentially fast. With a 10-layer network, you're going to see a lot of it. With a 100-layer network, by the time you get to the 100th layer, you're going to see nothing at all, except a few specks which blow up. So to give you an idea of how things work, here's an example on MNIST. We have, this is not a convolutional layer, this is just an MLP. We had something like 19 layers, each 1024 units wide. This is the output layer, this is the input layer, and the brightness of the image shows you the magnitude of the derivative with respect to the weights at each layer. And you can see, actually no, this is with the respect to the output of each layer. And you can see what happens. At the output layer, you get a lot of derivatives. They're pretty bright. You go back only 5 steps through the network. There's hardly anything left, right? So this is with a ReLU. Once again, you go back a few steps, there's hardly anything left. This is with a sigmoid. A sigmoid remembers things even less. 3 steps and you're gone. This is with a tanh, doesn't really remember anything. So all of these are for, this is with an ELU activation. In fact, you find that for the ELU activation is where the derivatives are retained for the longest depth through the network. But even here, by the time you get here, all the derivatives have basically disappeared. Now the thing to remember is that they haven't completely gone away. It's not as if any change in the input is not going to change the output at all. It's just that the majority of them have gone to 0. You have a small number, 3 or 4, which are so large that this thing is not simply not showing them up. But overall, the behavior is horrible. Now this is on the entire mini batch that you're trying to learn. Actually, this is on the entire training set. If I look at individual, what happens for individual inputs, again, these are for 9 different inputs with ELU activation, and you can see the same pattern happen. So this behavior happens both at the level of the aggregate of all of the training data and for individual training data. And this is with ELU. In general, what we find is that while ELU activations maintain gradients longest, in all cases, the gradients vanish after about 10 layers. They basically become insignificant. So what this means is that if you're using gradient descent to train your network, you take a batch of inputs and you pass your gradients backward. What's going to happen? Eventually, 10 layers down, the gradients are gone, right? You're never really going to make a lot of changes, corrections to the early layers of your network. That's something that you guys will keep encountering all the time when you train your networks. So this is a problem. And adding that to our story so far, recurrent networks retain information from the infinite past in principle. In practice, they are poor at memorization. We saw this going forward. When you're trying to remember things going forward, they don't really remember things for very long. When you're trying to compute derivatives going backwards, deep networks suffer from a vanishing or exploding gradient problem. And as it happens, recurrent networks are very deep networks. They're basically just very deep networks. How deep is the network? The depth of the network is basically the length of your input itself, right? And the input can be arbitrarily long. Now remember, in the last class, we wanted to ensure that any error that happens out here, it is actually the cumulative error of what happened over all the intermediate time steps. And we wanted to ensure that any updates we made to the network accounted for this fact. But if you look at what happens, and if you treat this as a regular deep network, what you will find is that you get gradient corrections for the first 2 or 3 steps. And then afterwards, there is no more effect going backwards, which means If you make gross errors out here, even then you're going to make absolutely no changes to the parameters at the early stages of the network. So this problem of vanishing gradients really comes to bite in recurrent networks. So we have these issues. Stuff gets forgotten in the forward pass. Each weights matrix and activation can shrink the components of the input, and stuff gets forgotten. In the backward pass, all the derivatives disappear, right? So we have a problem. 5 seconds, guys. Okay, everything was true. It was a very easy question, a pair of questions. You could have just chosen everything, because the derivatives for most parameters will become vanishingly small as we backpropagate the loss gradient through the network. The derivatives for a small number of parameters will blow up for the reasons that we just saw. Anything that's aligned with singular values that are greater than 1 will blow up. And the derivatives, but then here is the flip side of it. Why are these derivatives blowing up? What were the two reasons the derivatives were blowing up or vanishing? Can somebody wait? I'm going to call out two numbers, and then I'm going to call out a name. Who's 57? Nobody with 57. Who's 61? Okay. So there were two reasons we gave for the things blowing up. What were the two?
One is that the weights are above 1, and because of that, when
the weights are the singular values of the weights matrix is above 1, right? The recurrent weights matrix. Okay, and what was the other? The activations themselves, the nonlinear activations also cause things to either blow up or disappear in the backward pass, or to either blow up or disappear in the backward and the forward pass, correct? So who's 65? Anybody with 65? Okay, no one with 65. Then maybe James, you can help me. I have two issues over here. Well, which is I have one thing, I have activations which cause grief. I have recurrent weights. These are the two terms that actually cause the behavior of the recurrent network to fail, right? So now suppose you were an engineer, and I came to you and I said, I have this problem, fix it. What would you do? You can keep them within some range. There's a lot of extra logic, right? Suppose Occam's razor. Suppose I chose someone else of you. Who's 11? Okay, what would you do, Yukon?
You would try to make out something new.
Try to make out something new. Somebody else want to guess? Yes? You want to add some identity connections. All good answers. Anyway, the point is that we have this long-term dependency problem, both going forward and going backward. we want things to be remembered for a long time, but then we don't merely want things to be remembered, we want things to be remembered, we want some things to be remembered and other things to not be remembered, correct? And we want some things are just more important. Simple language, if I have something like Jane had a quick lunch in the bistro, then the next word should be she. And I've got to hold on to the fact that the person speaking was a female for as long as pronouns keep popping up. If I were analyzing a computer program, if I see an open brace, I have to wait till that brace is closed. And I have to remember that a brace was opened until the brace is closed. Otherwise, I'm not going to be analyze the program properly. But then once the brace is closed, do I need to remember that brace? So what does this tell me? What is the kind of behavior I want? One, you want arbitrarily long memory. And the second is input dependent, right? So you want this to be, you want what you remember to be dependent on how long you remember something to be dependent on what you remember. But then there's also the third thing. You want input dependent. This is recall memory and forgetting. You want all three of these behaviors. You want to be able to look at the input and say, I've had an open brace, and now I see a closed brace. I want to forget the fact that the brace was opened. At the same time, you know, until you see the closed brace, you want to hang on to the open brace. At the same time, some other stuff like this word a, who cares? You don't have to remember it for very long. The next step and you're done, right? So you want the memory to be arbitrarily long and conditioned on the input. And does our standard recurrent structure allow that? It doesn't, because memory is dependent on, what's it dependent on? We went through that. So what was the memory dependent on 54? Samruddhi, what was the memory dependent on? It was dependent on the weight, bias, and the activation. Does this include the input itself? No, right? And so these two were the two prime culprits. Now I'll give you one last shot to tell me how I'm going to fix this. I'll get rid of them. I'm not going to have activations because they hurt me. I'm not going to have weights because they hurt me. Pardon me? I get rid of those too, right? If I don't have activations, if I don't have weights, if I don't have, then if these are my neurons at various times, what is the nature of this network? What are the weights matrices if I say I don't have weights? They are all identity matrices. And what is the nature of this activation? Identity. So this is what I'm going to have. This looks bizarre, right? What kind of a network is it where I don't have any weights or where I don't have any activations? This is the kind of network that works. It's domain of mystery and magic, right? So the problem is the memory retention of the network depends on the behavior of these underlying terms over here, which in turn depend on the parameters of W and the activation function. So we want to have a network that just remembers arbitrarily long to be recalled on demand. So we want these two behaviors, and we want it to be forgotten on demand. So here's what we will do. We will have some network of this kind where you initially capture something from the input. That's the pattern you're trying to remember. And this function c of x0 will be analyzing the input to decide whether it is worth remembering or not. And then subsequently at each time, you're going to have something else coming in over here telling you whether to forget or not. So I would say I encountered an open brace, I'm going to hang on to the open brace, right? Then at each time, I'm going to say, is this a closed brace? If the answer is no, then I'm going to say keep the memory, right? And I'm going to keep doing this till eventually I get a yes, and then I forget. Is that making sense? Right? So now the memory behavior becomes input dependent. So here is the structure we will have. This is what we call a constant error carousel. This thing on top is the figure I have over here. You have C of t, which is the memory that is being captured. We have no weights matrices, we threw them away. We have no activations, we threw them away. All we have instead is that at each time we have a gate, some kind of a switch, which tells you whether to continue holding that memory or not. Right? Now, what are the things this gate would operate on? What does it require? What should it be looking at to make this decision? Who's 94? We've got to hand out the numbers in sequential order next time, right? We'll do that. Or do we have a 99? That's a very nice number. No? Do we have a 66? Okay, you are 66. Okay. So what would the things be that the gate has to look at? It has to look at the input, correct? So what else does it have to look at? What else does it have to look at? Does anybody else want to take a guess? The output. And what is currently being remembered, right? Whether you want to decide whether you're looking for a closed brace or not depends on whether you're remembering an open brace, right? So now, of course, you still need nonlinear processes in the network. So what will happen is that this constant error carousel just retains memory, which is turned on or off using switches. But then the output of this guy goes through some subsequent nonlinearities which influence functioning of the downstream network. So this is only the memory line of the network. And this guy, the gate, is going to depend on the output and the input, as somebody mentioned, as two of you mentioned. It's also going to look at other stuff. There may be other cues that you have missed. And of course, you're going to look at what's in the memory. Right? Is this making sense? How the whole thing was developed? Logically, it just makes sense, right? So this is what was called the long short-term memory. It explicitly latches information to prevent decay or blow up, and it does so by getting rid of the prime culprits, who are the weights matrix and the activation. If you don't have a weights matrix, nothing to worry about. If you don't have an activation, nothing to worry about, right? So here's what a standard recurrent neural network looks like. These recurrent neurons receive passed. So this figure is drawn differently, right? This is just the hidden state of a recurrent network. They receive the past hidden state, and the current input performs some process on it and then produce the next hidden state. This is how the standard recurrent network was. What the LSTM does is somewhat more complicated. It's going to be a structure of this kind, which looks very complex. But then if you pause for a moment and look at the network and see how it behaves, here are all the components of it. The first one is this main line, which has no weights and no activations. So this is the memory line, whose only job is to remember things. So that's what it's going to look like. But then it has two triggers. It actually has one multiplicative incoming trigger and an additive incoming trigger. So you could have constructed it in different ways. This was how the original LSTM design came to be, and it works. But the concept of having a memory line that's only influenced by the input and not by parameters or activations is the key part of it, right? So this carries information through. It's only affected by a gate over here, which helps it forget. and then there's an additive term which helps it remember. So for example, if you had one memory line to store braces, open braces, you need to keep track of how many open braces you've seen. So every time you see a new open brace, you want to increment. But every time you see a closed brace, you want to decrement, right? So there are two distinct operations. One of them which helps it forget, the other which helps it increment. They are not the same thing. Because the patterns that help you forget something or trigger forgetting can be different from the patterns that you increment. So if you're looking at open and closed braces to analyze a program, this guy would increment every time it saw an open brace, but it would decrement when it saw a closed brace. So these two are different structure. These two are different components of this entire line. So the gates which control the behavior are simple sigmoidal units with outputs in the range 0, 1. Ideally, they just be 0, 1. Remember this, forget this, right? But then you want to have something that's continuous if you're actually keeping track of counts. So it controls how much of the information is to be let through. So that's what happens over here. This is the constant error carousel, and the first thing that happens at each time is for it to be informed whether some component of what it has seen is to be forgotten. And that gate itself is operating on the hidden state at the previous time. Keep in mind the hidden state is not what is in memory, okay? And the input at that time. Then the next component is that something that tells it whether to increment what's in memory or not. Now here things get a little complex. There isn't a clear rationale. I mean, the rationale for it is not directly derived from the figure. You have one pattern detector, which is the tan H, which could, for example, be detecting whether something is a closed brace. But then you also have this additional gate over here, which multiplies the output of this detector, which tells you whether this whatever you have just sort of detected is worth adding to memory. So you have a two-component unit over here. Now you can it's presented in this manner, but the reality of it is that it's just a more complex activation function. The tan H looks like this. The sigmoid looks like this. This is 0, 1, minus 1, 1. The product of the two basically ends up looking like something like that, right? So this is just a more complex unit with a more complicated activation function. That's all. And now in the CEC, in any time step, there are two operations that happen. The first is an operation where it multiplies by the output of the first gate, which is called the forget gate. So the forget gate tells the CEC whether some of what's in memory must be forgotten or not. At the next step, you actually add the output of this unit, which in turn has two components. The first is the pattern detector. The second is the input gate. And the input gate is the one that decides how much of the pattern that has been detected should be passed on. So again, remember that the pattern detector actually is capable of giving you negative values over here. This is a tan H, right? So it's not merely incrementing, it could also be decrementing. So there's a second unit. And then finally, this is just the memory structure. It's holding on to things in memory. But then you need to perform some nonlinear operation on it to get your hidden state. And so the final component just transforms the memory through a tan H activation. And just because we like to make things a little more complex, you have something called an output gate, which multiplies the output of this tan H activation, which determines whether whatever hidden state we've computed is worth reporting on or not. So this is the and of course each of these gates, just the gates, also depend on what's currently in the memory, not merely the hidden state, not merely the input, but what's also currently in the memory to make their decision. So these things are what are called peephole connections. And so here is the entire LSTM unit. It looks very complicated, but then when you break it down and look at what is happening at each stage, it's not at all complex. There's a very nice and clean logic to the whole process, and this is built on the very simple idea that your memory structure should not be affected by weights and activations, which can mess up your ability to remember things or pass information backward. Its behavior must depend only on external stimuli, which inform it whether whatever it's remembering must be incremented or decremented based on the pattern that it is remembering, and also additional cues on whether it must be forgotten based on other patterns, like a closed brace. So if this were remembering an open brace, these would be incrementing or decrementing braces. This would be telling it whether it's encountered a closed brace. Right? So I'll stop over here. Any questions? Yeah.
So does the gate have, because like the gate has some weight and bias, so doesn't mean like the gates will depend on the like activation and also.
So the gates are going to, each of those gates, I have the equations for each of these gates. We'll go over this again in the next class. These are just, the gates are just standard neurons. So yes, they will have activations. The gates will have sigmoid activations and affine combinations of the input. Yes, Oren?
It's not clear to me why sometimes you use sigmoid and sometimes you use tan H.
So tan H is being used for a pattern detector. Typically, the sigmoids are gates. Goes between 0 and 1. Reduce the memory, increase the memory. Tan H are pattern detectors. I found one more brace, right? Or decrement the brace count. So that goes from -1 to 1. Right? So the distinction between the two is one is bipolar, the other is unipolar. That's it. And of course, for this guy, we found that having the hidden state be operated on by a tan H sort of was useful in terms of memory, although in this particular setting, it's not clear that that's that important.
Okay, so it's more empirical in that case?
In this case, it's more empirical. But in the standard RNN, there's a very clear reason for it. The tan H remembers longest. Yes, Jeffrey?
Why are we using a gate for the output, the OT?
Because we like to complicate things. Right. So some of it is not explainable. The basic ideas, the basic concept is simple enough. The actual implementation can be quite bizarre, right? All right, guys, thank you.